So it's a pleasure to present the work we've done in cooperation with majorly the Technical University of Munich and Franz Geiger's team. And we were looking into simple and advanced modeling methods for the fish passage through the turbine, and especially looking in operation modes of the turbines, and also try to include fish behavioral aspects into it. Okay, I think go briefly over this just to remind you back what's happening if a fish passes through a turbine. There's different things which the fish can experience. There's different obstacles. So it's the problem of collisions with the stay-winds, wicket gates, or worst case with the runner. Then for Kaplan units, there's gaps which can be critical for the fish. And what we heard just before is there's the major pressure change from passing through the turbine, and there's very low pressures the fish experience close to the turbine, and if can even be below the vapor pressure, and then cavitation initiates. Also, there's shear stresses when there's large gradients in velocity in corners, and of course there's a lot of turbulent flow, especially then in the draft tube. So when we want to model what's happening for the fish through the turbine, we first have to know the physical load on the fish. Then we should need the information like how the fish can handle those load. And finally, out of this, a survival rate can be estimated. Okay, so what was done in the FIThydro project? We had several test cases, like for the Guma power plant and the Bad Bill power plant in Switzerland and in Spain. And also there was live fish tests and laboratory of the University of Munich in Obernach. And for all of these three test cases, Jeff was and his team were putting sensors through the turbines. So we wanted to improve the fish modeling by using the input from the test cases, and also calculating not only one operating condition, but looking at the whole operating range of the machine, how the machine is operated over the year, and see how this influences the survival rate. Also, the idea was to look into fish behavior, how this has an influence on survival rates. And finally, we're looking into biological response data, what was available in literature. So we didn't create anything new. Okay, and this ended then first in some simple modeling. So depending on at what where you are at the project, you have either getting simple modeling and later CFD-based modeling to get more into detail. So first, some findings from the field test validation. So from the experiments in Obernach, we could get some fish data for such as it's a very small turbine, this shaft turbine. So the major impact is a strike assessment, and then we could model this strike assessment for the operating condition, which was the machine operated while the test. We realized there's a shift in the results for the survival rate here. So it's fish length over survival rate. And then in literature, we could find information that from studies in the US, majorly that the tail region is rather unsuspectable to injuries. And correcting the length of the fish matched the curves then pretty well. Secondly, we got these from the sensors. We got the like the pressure change through the turbine. You can see it starts slowly approaching the turbine. Then through the turbine, there's a minimum pressure reached. And as we learned before, in the end, the difference between the acclimation depths of the fish before entering the turbine and the nadir pressure, like the lowest pressure the fish experience in the turbine, can be very harmful. We used the BioPA approach and then correlated this to a CFD path, which in a certain scattering was representing then the sensors, and got a fairly good agreement, having in mind that the sensors not always pass in the same regions as we expected in the first place. So first, I want to go then to the simple modeling. So simple models are mostly based on physical or empirical background. So most models are strike models. So you see here the turbine blade, and that's the velocity a fish approaches the turbine blade. And then you can put into relation the time a fish needs to pass by the blade versus the time from the one blade of the turbine to the next turbine until the next blade of the turbine arrives. And in this time, the fish needs to pass. Otherwise, we get a strike event. And into this, the number of blades, the rotational speed, of course, the discharge in the head of the operating condition, also the size of the machine, and of course, the length of the fish is going into this. This model was then extended to also look into orientation of the fish and potential swimming speed of the fish. So we could then, with the strike formulation, put more variables into that. Also, there was it was realized that a lot of models use empirical flow angles and velocities, and this can be improved by using a turbine hydraulic machine guidelines, and this is also in the deliverable 3.1 included, so you can get a better estimation of the actual flow angles which are existing in turbine, so the fish is passing by the turbine. And finally, some biological response functions can also be included already in these simple formulations. For example, the speed a fish can withstand in a strike event for the impact velocity. Okay, now quickly, how is the CFD-based modeling working? So basically, a calculation of a turbine is made, and streamlines can be extracted. On these streamlines, assuming a fish is neutrally buoyant following the streamlines, the pressure, shear rate, and flow velocities can be extracted. Flow velocities are used for the strike modeling, and the other values, the minimum value is extracted. Then we get a probability, that's the blue curve, that a certain, in this case, pressure occurs. And this is put into relation into what the fish, how mortal or injurious this is for fish. And then you get a certain amount on this curve there. And this is when a fish has a mortal injury caused by the passage through the turbine. Okay, this approach was then realized to be used for the Skooma and Banville power plant. We ran all possible operating conditions and even further to get these fish passage hill charts Peter already presented before. And we could get those for different stresses then, for the pressure, minimum pressure, the shear, and for the strike events. And you can see, for example, strike for high flows, the risk of strike is lower because there's higher velocities and the blades are wide open. And for pressure, the higher the flow is, the lower the pressure gets, so it's a bigger risk for the fish to get injured. So yeah, then this can be then combined to one hill chart in getting a operational scheme which is preferable for fish versus what normally is done for the economic way, having an efficiency hill chart. And this then can be put into relation and decided how to operate the machine, for example, in migration periods. Okay, the second part, besides the hill charts, was trying to bring these behavioral aspects into the modeling. So we naturally looked into the fish orientation in relation to the turbine, the swimming ability, so if the fish is actually swimming against the flow, or the passage location. You can see here below, we looked at the three regions, close to the hub of the machine, in the middle region of the machine, and at the outer region of the machine. And these, you can see here the different stresses, strike, pressure, strain. Especially for strike, it can be stated that for the outer region, it's much more risky if a fish passes through there, as the velocities are higher and also the blade shapes are, for conventional blades, are very thin. The fish orientation, we can see here for 0 degrees, which means aligned to the flow, is almost the worst case scenario, and this is normally what is used in the modeling. And changing the orientation could be beneficial for fish passing through the turbine. The good thing is now we can quantify those effects. Okay, so what did we learn in this project then? We can identify relevant stresses during a fish passage and quantify them, and also with the CFD approach, localize them. And also we have some biological response data available, of course, only for some species, and it needs to be seen if this covers all eventualities. But as but it's possible now to make a turbine design using those information to reduce the impact on the fish. And also you can do this with a relatively overviewable effort, depending on how complicated the modeling is made. Also, we have the capability now to make a hill chart, not only looking at the power of the machine, but also looking at what does it do to the fish. Secondly, we looked into impact of fish behavior, and we could see, yeah, that there's some impact for the fish, how it behaves in the turbine. At the moment, it's still complicated. I'm not 100% sure what's happening exactly in front of the turbine, so this requires further investigation. But anyhow, we can now quantify behavioral aspects and model those when we make those analyses for the survival rates. And last but not least, this means then in combination with guidance structures, this can be like bar racks or also behavioral aspects combined with an improved turbine design for fish passage, very high survival rates can be achieved in turbine passage then. Okay, so then thank you for listening to my presentation, and thank you all the partners which contributed to this project, especially also BKW and Savasa for giving us the data for the power plants and all the input. Thank you.